Good morning, one and all. Welcome to another episode of Physics. It's Mr. Finn coming at you from neighborly Northville. Hope everybody's doing great today. Come to the end of a long week. I'm sure you're doing a lot of work. I just have one little thing to talk to you about today, and that's on transformers. Transformers are unique, and they will allow AC power to be changed to a different form of the same power. In other words, the voltage could be changed between part A and part B. How are we going to do that? We're going to make use of Faraday's law. We're going to send current through a coil of wire. Let that current induce a magnetic field in a core. Somewhere on the other end of that core, put another coil of wire and take a different amount of current off the other end. Now, how does that happen? Well, maybe a picture would help us understand. So we're going to go to the big board right away. But this is not a long lesson, guys, so just stay tuned and we'll get through it quickly. All right, let's go to the big board. Okay, guys, here's what we have here. Transformers use magnetic fields as a way of transforming the power, stepping it up, stepping down, change the voltage for a specific use. For example, your phones. Your phones operate on something less than 120 volts, but yet we plug the chargers into the wall. What are we getting out of the wall? 120 volts. But how are we changing the power? That, my friends, is part of that charging block. Inside that charging block is a little transformer that makes the power different when it gets to your phone. So, some kind of current. I don't know what kind of current it is, but we know it's 120 volts. This purple line, and that's going to be a coil wrapped around an iron core. It's just like an iron cube with a hollow part in the middle. But in this iron core is a pulsating or changing magnetic field. Now remember, AC was alternating current, so the oscillations occur about 120 times a second or 60 hertz. That's how often that little spindle is moving around and oscillating the current. Okay, so this changing magnetic field will produce current in the second coil because that's Faraday's law. It's just like the magnetic strength is changing in the coil, the second coil. Now, if this were hooked up to a DC supply, the same thing would not happen. If you hooked up these two lines to a battery, that battery would only produce a pulse in this magnetic field one time when it's being connected. Otherwise, it would just be a static magnetic field, and that would not produce current in the second coil. We need a changing magnetic field. As a result, current will be produced in the second coil, but different current than in the first coil, based on the fact that the number of loops are different. For example here, I've got 120 volts connected to my primary coil. The number of turns is 100. That means there's 100 turns on this part here. I've got 300 on this coil. Secondary turns, 300. What would be my final voltage that I measure on the secondary coil? Let's have a little think about that. My friends, the voltage formula is V1 over T1 is equal to V2 over T2. Now, if we're looking for V2, we're simply going to multiply T2 on both sides. T2 will cancel over here, and it'll be T2 over T1 times V1. So 300 turns over 100 turns times 120 volts. 300 over 100 is 3. 3 times 120 is 360 volts. So there'll be 360 volts available on the second turn, the second loop, right here. Now you might be asking yourself, Mr. Finn, is that free power? Did we get an upgrade in voltage for free? No, we didn't. Remember, conservation of energy still applies. So if the voltage went up, that means my current had to to go down because the product of voltage and current is power. So the same power comes into the transformer as comes out of the transformer. It's just the way the power looks that's different. So a transformer can step up voltage, or it can step up current if you had a reverse coil situation going on. But a transformer cannot change the amount of power in or out of the system. That, my friends, that's still conservation of energy. And that's still a law we learned back in October. It's still applying here in this time. So guys, from a mathematical standpoint, the mathematical relationship of a transformer is relatively simple. But there are some practice problems I'd like you to try. The hard part is understanding that power is the same in and out of the transformer, but the way the power looks can be very different based on the fact that we can step up voltage or step down voltage. A step-up transformer is one that steps up voltage, like our example here. A step-down transformer might be something that you see in your phone's charger blocks for your phones. That would be a lot of loops at the beginning and very little bit loops at the end, trying to step down the voltage. Okay, guys, let's wrap up. Okay, guys, so let's wrap up. We had motors and generators. We had Faraday's law, we had the process of electromagnetic induction in general, and now we have transformers. There are 2 additional videos I'd like you to watch on how those transformers work. But this is our wrap up of magnetism and electromagnetic induction. I'll have a final thought on that in a video on Monday. But for today's Google form, guys, basically your homework questions, magnetism, current in the wires, let's talk about motors and generators, let's talk about Faraday's law, and let's talk about transformers. If you have any issue, please let me know, but I'll have a Google form ready for you today. Remember, transformers can step up or down voltage, but they can in no way change the amount of power or energy that's used in the system. It's all just how the energy looks. Have a great day, guys, and we'll see you next time.